So good morning everyone, and thank you for staying till the end. Okay, I first thank the organizer for inviting me in such a wonderful meeting and present our recent work. So today's topic is something like a 2D ferromagnet, like a very interesting ferromagnet like Fe4GeTe2, which is like a near room temperature van der Waals ferromagnet. And what I am going to discuss something like a these ferromagnets shows very unusual properties like if you reduce the temperature, the easy axis of the ferromagnet goes from in plane to out of plane, and this is something called a spin reorientation transition. Although spin reorientation is not a new phenomena, but in these material I will show you some unusual phenomena which arises in this material system. And primarily I will be talking about the PhD thesis of my student Dr. Riju Pal, and also they like my previous postdoc Dr. Buddhadev Pal, who also helped in developing all these transport measurements, doing transport measurement, and Doyal also at the end he joined in Raman spectroscopy part. And before starting the talk, I would like to thank my collaborators. We intimately collaborated Professor Prabhat Mondal, who has also grown the sample. Then Tanmay Das from IISc did some theory part, and I'll discuss also ESR measurement with we have a MOU with IFW Dresden, and there my student went there and did ESR measurement to directly measure the anisotropy in this system. And Professor Achinta Singh for Raman spectroscopy, some measurements, and Devjani Karmakar on doing some calculation as well. And also I would like to thank the technical cell facilities at SN Bose Center and TRC facilities of SN Bose Center, and of course DST Nanomission for funding. Okay. So before going to the talk, I will just briefly describe what we do in my lab. So my lab is called Quantum Transport and Devices Lab, and we focus on various things on quantum transport, from like 0-dimensional single atom transport to a bulk transport, 3D like transport. So this is like we have developed something called single molecular break junction setup to understand transport through a single atom or single molecule. And then we are also looking at emerging materials, like particularly recent focus is various charge density of material, where you see a charge density of transition, and as a function of charge density of transition we want to probe various kind of emergent transport features. For example, it can show like a planar Hall effect, it can show superconductivity or even weak ferromagnetism in this kind of quasi 1D material, or even this classic charge density of material we also found nonlinear Hall effect. Okay? So these are various transport based probe we use, and also we looked at the device aspect like 2D semiconductor, like or hybrid devices like light matter interaction based devices, or like 2D p-type 2D semiconductor to understand the defect or defect dynamics through transport and noise measurement. Okay? So with this introduction I will go to today's topic. So today I am going to talk about this 2D ferromagnet. So till 2016 like in 2D family, like almost all the material was existing, like material properties were existing except the magnetism. Okay? So till 2016, and of course people predicted that because of the Marmini-Wagner theorem, which states that thermal fluctuation destroy long range magnetic order in the 2D systems, and you do not expect a long range order, right. So, but in 2017 back to back Nature paper where they described that even in the monolayer limit you got ferromagnetism. Okay. So why it is stable, this ferromagnetic state is stable. So then this main thing is the magnetocrystalline anisotropy, which actually stabilizes this magnetic order. Okay. So in brief, this magnetocrystalline anisotropy you can understand like iron, like if I take iron in our system we have iron. So iron has all these different orbitals which are degenerate, but if it is in a crystal you have a particular symmetry, crystallographic symmetry, and also you have spin orbit coupling. Now spin and orbit you can understand like spin S, like a L DOS S kind of term, like L, like it couples crystal with the spin. So that's why crystallographically structure and spin orbit coupling can like a favors like can change like break this like degeneracy, and it can provide some kind of easy access to this system, and that is something called the magnetocrystalline anisotropy. So I will discuss this role of magnetocrystalline anisotropy is important in this kind of lower dimensional magnet. Okay. Okay. So today's plan is I'll tell 3 different kind of experiment. One experiment is that I'll show you the unusual transport phenomena what we observe in this kind of 2D ferromagnetic device. Then I'll show you direct measurement of anisotropy using something called ESR spectroscopy. Okay. And then finally I'll show the result on Raman spectroscopy, which talks about the spin lattice coupling in this material. Okay. So this 2D kind of thin layer, it's not an old topic. People are trying in a like since long time to get 2D what will happen in the 2D limit. So this is one of the very old papers where ferromagnetism in ultra thin films down to 5 nanometer people have studied, and they found that like a TC actually decreases with thickness. Okay, like TC typically you in 3D limit you just get like 1000 Kelvin around for iron or any kind of this typical ferromagnet, which you can determine only through the exchange coefficient J, right? Exchange interaction coefficient J. But whenever you are making a thin film, this magnetocrystalline anisotropy plays a role, and this K comes into the picture. Okay. So then the TC will be reduced by something like this kind of equation, J by ln log of some 3 pi by 4K. So then this people are trying to understand, like after this discovery of van der Waals ferromagnetism, like CRI3 or this kind of CRX3, this kind of family, they found that the TC is very low, like 30-40 Kelvin or 60 Kelvin in this range. So what people are trying to see, they're trying to increase the TC. One idea to increase the exchange interaction J. So how we can increase, like you take a, like you want a van der Waals kind of structure so that you can go to thin down this layer. So you take a MOH2 kind of TMDC structure, okay, TMD structure, like a MCH2 kind of structure, and then you try to incorporate iron or this kind of ferromagnetic material element in this material. So if you incorporate iron and you want to, if you can make this kind of structure where in the unit cell you have iron, and still you can keep the van der Waals structure intact. Okay, then people found that you can make 3 kind of this kind of material. You can form FeNGET2, this kind of structure you can make, and if you have 3 iron in the unit cell, people have till now people have found 3 version of this, like Fe3GET2, Fe4GET2 and Fe5GET2. And interestingly, in all these 3 material what they have synthesized, that the TC has increased enormously. Like it has, for example, if you are basically like 3D like exchange interaction, keeping the van der Waals structure intact, and you can see the TC of this material. Like Fe3, you have a TC of 210 Kelvin, and where Fe4, what I will be talking about, here there the TC is 270 Kelvin. So all near room temperature. So Fe5 even has a TC above, slightly above room temperature, 310 Kelvin. So this is already very interesting, and like people are thinking now, like if you can make a large area of this sample and you can make devices like which operates at room temperature. Okay. So also people could found the anisotropy of this material, and the TC you can see as you are increasing iron, the TC is increasing. Simple logic is that you are increasing the exchange interaction. Now people have done the detailed measurement, and one more interesting properties of this van der Waals material is that you can reduce the thickness, and if you can reduce the thickness, you can actually get the material, you can think about different kind of devices, and you can study various phenomena like how the anisotropy changes and all these different things. So these materials have been studied as a function of thickness, and they have found down to not monolayer but down to 7-8 layer the magnetism still exists. Okay. So, with this background I will just briefly tell about other sister family like Fe3. What is the property? So, this is the typical magnetization curve of this Fe3GeT2. You can see that there is a ferromagnetic transition, and then it slightly behaves like this, and it increases. This is some anomaly will be there, and you can, it's like a easy axis ferromagnet, like the easy axis is in the c direction. But if you take Fe5GeT2, if you see this magnetization curve, like if you can think about typical iron or other kind of ferromagnet, it should go as T minus Tc to the power 3/2, right? So it should be very monotonic. But you can see in this material already the magnetization behaves differently. So there are some other kind of interaction is already present there. So in this material there are already lot of work, and people have shown that this is like a easy plane ferromagnet. So you are actually changing the symmetry of this material as well, and also the magnetization easy axis. Okay. Now let us come to the material what we will be talking about. We are talking about this Fe4GeT2, and there are 4 like iron atoms, and these iron out of these 4 iron atoms, 2 are inequivalent iron atoms. Okay. And very interestingly, if you see this magnetization curve, this also behaves little unusually near this point, near like this is the Tc of 270 Kelvin, and you go there and there is a peak here, and then this is the magnetization measurement when magnetic field applied in plane, like you are applying magnetic field in plane, the red curve, and blue curve is out of plane. So you can, if you reduce the temperature, very interestingly you can see that magnetization actually decreases, and then after some point like around 120 Kelvin or 110 Kelvin or so, you can see there is a change of magnetization, like magnetization in the C direction goes above and magnetization in the AB direction goes below. These are not done simultaneous measurement like one after another. Now if you take the MH curve, you can see that at room temperature, MH curve shows that the this curve its opposite coercive field is opposite than the at room temperature, and low temperature for C direction, this is the red curve is the MH curve. Okay. Then you can see that it reverses the signature, the anisotropy reverses. So that means this easy axis actually changing when you are going from room temperature to low temperature. So room temperature the easy axis is in plane, and low temperature the easy axis is out of plane. And I already discussed this easy axis actually depends on the competition with the magnetocrystalline anisotropy. Like there are different kind of anisotropy. One is the shape anisotropy and the magnetocrystalline anisotropy I also already told. Here also shape anisotropy is also very important. So it's kind of a question is that whether it's a competition between shape anisotropy or magnetocrystalline anisotropy. Okay. So this is work from Dr. Mintu Mondol's lab. They already have done the specific heat measurement, and they showed already in the specific heat also there is some anomaly in the transition. So it's a thermodynamic transition. Okay, that has been proven. So with this background, now let's go to our measurement. So first of all, these measurements, these materials, like in the previous talk also you heard about WTE2, all these materials are fine in the bulk limit. But when you are going to the device limit, when you are exfoliating, these materials are very difficult to contact, like getting electrical contact is actually difficult. So what we have done, we have developed this heterostructure like dry transfer setup, and if we just do lithography and all this measurement, then will not get any contact on this device. So what we have done, we have prefabricated the contacts, and these materials we found that it is stable up to, let's say, half an hour, 1 hour time, it is more or less stable. So after several trials, what we have done, we have just made the contacts, and then within half an hour we exfoliate and put the flake using this dye transfer setup, and then we encapsulate with PMMA or some other resist. Okay. In this way we found that it can provide a good electrical contact, and we have done measurement of a few thecal layer like 16 nanometer to bulk limit like 95 nanometer. These measurements we have done. It's not like graphene that you can exfoliate very easily, but it's exfoliable. Okay. So let's go to the resistivity versus temperature curve, and you can see this black curve is the resistance versus temperature curve. And very interestingly, you can see that 270 Kelvin is the ferromagnetic transition, and in resistance almost there is no signature. Okay. But whenever it is crossing this 120 Kelvin or 30 Kelvin, in this range the resistivity decreases suddenly, and it actually becoming more metallic, right, its resistance decreases. Now if you just take a derivative of this curve, you can see that near 270 Kelvin there is a very weak signature, that and near the spin reorientation transition the signature is very strong, like you can clearly see that resistance decreases rapidly, and on top of this we see a hump around this 38 Kelvin. I will discuss more detail about this 38 Kelvin part because we see it repeatedly. Okay. Then we try to understand the temperature dependent resistivity using this simple all these component. So in a resistance versus temperature, you have all these different component. You can have residual component, you can have electron-electron interaction part, and electron-phonon interaction part, or you can have electron-magnon interaction part. Now this low temperature part, you can see that you can actually fit with T square. It's like a Fermi liquid kind of behavior, and you can see that 40 Kelvin there is a hump I told you, right. In the previous graph I showed you this this hump, and you can fit this T square curve till 40 Kelvin. And what happened in this region, intermediate region, it goes as T plus T square. Okay. And in the high temperature range it goes as proportional to T. Now interestingly, this T proportional to T term you can get either from T square term, here this T square term you can get from electron-electron or electron-magnon, both gives T square. So how to decouple this? What we have done, we have, okay, this is verified in other device also. What we have done, then we have applied magnetic field. Now electron-electron and electron-magnon interaction you can decouple by applying magnetic field. Electron-electron interaction typically should not change with magnetic field. If it is electron-magnon, then it will be suppressed by the magnetic field. So now if you look at the data here, this is the magnetic field plus minus 9 Tesla we applied, in this black one is 0 Tesla and other is plus minus 9 Tesla. Now you can see till 40 Kelvin this does not almost change. So this is kind of pure electron-electron interaction. Now if you go 40 to this near spin reorientation transition, you can see there is a huge change with magnetic field. That means there the electron-magnon interaction is important here. So this regime, the electron-magnon actually dominates. So it's not a pure electron-electron interaction. So electron-magnon and electron-phonon are dominant in this case. Okay. So that is what we have decoupled this one. Then what we have looked into, the Hall effect, like in this system, like as you know in this magnetic system, if you measure the Hall effect, you can have both this component like the ordinary Hall component where you can get the density, and other one is the anomalous Hall component which is proportional to the magnetization of this system. Okay. So now we have decoupled all these parameter, and then before that I'll talk about the first the Hall data. So let's talk about the ordinary Hall component. Now if you take the ordinary Hall means it's the density, right. So if you see the density, you see that density is more or less constant, then near the spin reorientation the density changes sign, like it becomes from electron to hole. And another thing, this is data from both the device 16 nanometer and 95 nanometer device, and in another case you see near 40-50 Kelvin there is another transition in the density, right. So that means here it's again the density changes sign. So that means there are two Fermi surface reconstruction happening near these two transition. One transition was not reported, this is 40 Kelvin, and another transition is already like a spin reorientation transition. So then before that I will now go to this magnetoresistance data. So if we look at the magnetoresistance also in a like a ferromagnetic system, if you apply magnetic field, you can actually reduce the spin flip scattering. So, magnetoresistance typically you expect negative. Okay. So, if you see the magnetoresistance, it is actually maximum negative maximum near the spin reorientation transition what we find, and above this, below this 50 Kelvin, the magnetoresistance is becoming positive. So, positive magnetoresistance means it is like a metal, like a Drude model. If you just see like a it behaves like a ordinary metal. So, here the orbital part is important and it suddenly become positive. So, till now what we have found, we discussed two effects. One is the Hall effect and another is the like the magnetoresistance. In both of these signature, we find that there are two transitions happening in this system, and the second transition we do not understand what is the origin, but there is a transition. Okay. Now, we have done all the scaling behavior in the details. I will not go into the details whether the skew scattering and all the other 5 minutes. Okay. So, I have to go fast. So, then Tanmay actually did the calculation and they could explain there are two kind of states, like one is the collinear state and one is the non-collinear state, which are there and which are important, which can explain these two transition. That is what, although it is not complete, but they could explain to some extent. Okay. I will now quickly go through this electron spin resonance study. So, this is the electron spin resonance, like if there is an isolated spin, if you apply magnetic field like a MSc experiment what you have done, you can detect, you apply a AC magnetic field and you can detect the resonance through which you can actually detect the isolated spin. Now, if you have a if you have actually, this experiment was done at IFW Dresden. So, if you have an ordered state, now if you have an ordered state, if you apply like a magnetic field, the spin, this ordered state will precess and you will have this kind of ferromagnetic resonance, right. So, important thing is that if you have only isotropic ferromagnet, then you have a constant like a resonance peak which will be dictated by the paramagnetic resonance field, then it will be dependent only the H external. Now, if you have an anisotropy in the system, then your resonance field will shift. Okay. I will show you the data, then it will be clear. You can actually solve this equation for a easy axis ferromagnet or easy plane ferromagnet, and you can actually calculate where will be the resonance field. Now, let us go to this data, temperature dependent magnetoresistance like ESR data, and you can already see these are the resonance the frequency magnetic field resonance point, and you can see if you scan this ESR spectra, you can already see this point at low temperature, this is in the left side. Okay. Now, if you go to this near spin reorientation transition, it is actually hitting the paramagnetic limit, but if you go above, this is moving to the right side. So, truly speaking, that means the anisotropy actually changing as a function of temperature. That is actually very interesting. So, we have verified with various other frequency and various other direction like in plane and out of plane. If you do out of plane in plane measurement, then you can see this will be in the opposite side. So, we can actually directly measure the anisotropy field. Okay. So, then I will go to this graph, which is important, the result graph. So, then we can actually decouple, this is the ESR spectra like the total anisotropy field as a function of temperature. So, this is the raw data, and then what we have done, we have decoupled this like a two factor, like a magnetocrystalline anisotropy has two factor, like so total magnetic anisotropy has two contribution. One is the magnetocrystalline anisotropy, which is dependent on the spin orbit coupling, and another is the shape anisotropy because of the shape of the crystal. Now, shape anisotropy you can get from some estimation you can do from the magnetic data, magnetization data, it is monotonic. So, you can get some estimate of the shape anisotropy from the magnetization data, and if you decouple this, then we found this curve. So, you can see as a function of temperature, if you are lowering this temperature, this magnetocrystalline anisotropy has a strong increase. So, and it is a gradual transition, it is not a sharp transition. Spin reorientation people have found before, and there are some transition called as the Morin transition, which is the first order transition. So, it looks like it is a second order transition, and below this 50 Kelvin actually you cannot this anisotropy field is dependent on the field orientation, which cannot be explained by the standard ESR equation. Okay, till now this is the understanding, and I'll just give me 2 minutes. I'll just explain this Raman spectroscopy data. So after establishing this ESR data and transport data, which matches very well and dictating two different transitions, we wanted to understand whether there is a spin lattice coupling if we can get any information from the Raman spectroscopy. So we have done the Raman spectroscopy measurement and we can identify different mode. Dr. Devjani Karmarkar's group could calculate this Raman mode, and interestingly they found various kind of mixed mode in this system. But I'll go to this temperature dependent data. Now if you reduce this temperature, there is a actually you expect these Raman modes like a hardening as you are lowering the temperature. But near the spin reorientation transition, we found a softening, and that is kind of signature of the spin phonon coupling in this system. So although this near the ferromagnetic transition there is not much effect, but near the spin reorientation transition it's another magnetic transition, there the effect is pretty high. Okay, and we have done all the detailed calculation how the Raman modes is there in our archive paper. And actually they found also this theoretical calculation, they found also Magnon modes below this Raman, like below the spin reorientation transition through atomistic spin dynamics calculation they have done, and we are certain that there is a strong spin phonon coupling near the spin reorientation transition. Okay, so with this I'll go to the summary. So what we have done this transport measurement, ESR measurement and Raman spectroscopy measurement. What we learned? We learned that in transport we found actually this is a resistivity curve. There are two transitions we can detect, TSR and TQ, and then Hall measurement shows also that there are two transitions because there is a Fermi surface reconstruction. And then ESR measurement also tells that the anisotropy behaves differently, like there is a strong enhancement of the magnetocrystalline anisotropy which is probably driving this spin reorientation transition, although the origin of this enhancement is still not clear because this requires more theoretical understanding of this material. And below this 50 Kelvin there is a deviation from this normal ESR equation, like I showed you this Landau-Rydberg equation, and that actually deviates. So that also we do not understand why this occurs, but there is a transition. And actually I have not shown the XRD spectra, XRD measurement. XRD measurement could not detect any kind of structural transition. There is no detectable structural transition. So that is why we did Raman spectroscopy, and Raman spectroscopy shows that near the spin reorientation transition it strongly couples, like a spin and lattice strongly couples, and it can soften the phonons. Okay, and with this I'll just summarize, like Tanmay did the DFT based calculation and they found two phases, and these are actually published in these materials in this literature. And with this I want to thank you for your attention.
Wonderful talk. So you haven't mentioned the shape of the crystal.
It's a Van der Waal crystal. So it's a bulk crystal we have taken, and you can actually ESR measurement was done on a bulk crystal.
But you are assuming 2D limit for the matrix, which is not correct because you have a
So ideally you should. So we are actually trying to do on a thin layer like EDESR, that is probably required to do a thickness dependent one. So this demagnetization, this shape anisotropy estimation, actually it's a kind of overestimation. It's from the magnetization data. It's not a actual estimation. I understand your point. So that's not an actual estimation, but this non-monotonic behavior you can explain from this shape anisotropy part.
Another thing is, why do you need this ESR? Because it seems like you did just the anisotropy measurement on that. But you can do also the magnetization measurement, right? What is the need of ESR as such?
Yes, but ESR can directly probe the anisotropy, right? And directional magnetization we have already done. Magnetization also.
No, you have this external collaboration. That's why you used it.
No, not like that. So magnetization was already done with Professor Prabhat Mandal, and he has already published this detailed magnetization measurement. Yeah.
Hi.
Yes.
So I had 2 points. One was regarding your fit of the resistance
Mm-hmm.
data.
Mm-hmm.
So the low temperature, I was surprised you've not done any block horizon fit there. Why? I mean, you're saying that it's T square, but T square is like really at a
Very low temperature.
very, very like millikelvin.
Yeah, but not millikelvin. It's it T square fits.
If you do a R naught plus alpha T fit in that range,
It will not fit. We have tried that. We have tried.
you've not done a block horizon fit in that range?
We have done proportional to T. You mean, right?
No, no. Block horizon is T raised to 5.
Yeah. That we have done. That we have done, and it doesn't fit. It actually doesn't fit with this data. We have checked that detail. I have not shown in here. I have mainly presented this T square part in the low temperature part.
And then you're saying that
Mhm.
like where is
Just sorry.
that's just the watt limit, no?
Sorry.
I mean the resistance, the temperature where it is saturating, that's just the watt limit. I mean it looks a bit tilted, but
Let me go to this data once more. So yes, this one, right?
yeah. I mean I'm very
Mm-hmm.
your fit here,
Mm-hmm.
the T square fit looks very, I mean I would be very surprised to think that it will not, where you're saying T square, T plus C square,
Here.
that whole range, it will not fit. Block horizon looks very surprising. I mean,
Okay, we can actually you mean T to the power 5, right?
yeah, I mean in the low range
It will be T to the power 5.
where it more or less goes linear, and the place where you're showing that it is actually going directly as C, that is just the Mach limit, no? I mean,
Here.
it's flat, but it's having a little slope, but that's above it.
You mean here?
Yes.
No, here we have not. I understand. Here we are not concentrating more, so we are more concentrating here. Actually, there that we can discuss this fit. We have not. This is more or less linear. What we found.
Yeah. So this is one point. And so when you're saying that it's an electron magnon or I don't know whichever magnetic positive particle interaction,
Yeah.
which one? Because from your magnetization data, I was not sure what is the ground state. Is it like an antiferromagnet or you showed some ferromagnetic
It's a ferromagnetic ground state. It's a ferromagnetic ground state, but low temperature part it's a non-collinear. That's what people have found.
But ferromagnetic at higher temperature.
Higher temperature ferromagnetic. Yes, there is that is still not understood very well. This people have not done neutron experiment or in this material, so they could not do yet this neutron measurement.
So in your fit now, which is the electron magnon part?
This part. This part. Because I am telling from this measurement.
I think you should refit your data.
Okay, we can discuss. We can discuss this. Yes.
We have two more questions. Sorry, so we are running out of time.
I think very good talk. I just wanted to know a question. Because a initial paper which you cited earlier.
This magnetization thin layer. Okay.
This time, as you reduce the dimension, the TC decreases because the number of pairwise interactions is decreasing.
Okay.
That is what the idea. Number of pairwise interactions. I cannot understand why the anisotropy will reduce the TC.
So there in the thin limit, maybe I have to read the paper again. So in the thin limit, they are saying that the anisotropy becomes very important. Like, so you are expert of that. So that. Sorry, you mean this one? Okay.
No, it's anisotropy in this kind of material. Before the magnetocrystalline, is there anybody people talking about external anisotropy? In this kind of process?
So which material you are saying? In this,
Particular, let's say this or this kind of this material.
in FGT kind of material or van der Rohe magnets? What anisotropy you are saying?
Exchange anisotropy.
Exchange anisotropy. So that still not understood. Not I don't know. Means I am not. So till now there is no direct. There are not many direct measurement of anisotropy. So what I know that there are ESR measurement on these material, few measurement were done, but exchange anisotropy direct measurement I am not sure people have done it. Maybe we can discuss more in detail here.
Very quickly, since we have one absentee, so maybe we can spare 2 minutes for questions.
In your ESR data, there are
Mhm.
for a resonance there should be one dip, right? But it looks
Ah.
like there are two dips.
Yeah. So that's the unusual thing. Still, I'll go to this data. So I'm not expert in ESR, but people have like my student went there and did the measurement there. So you are saying these dips, right? These are actually, as I was telling, this even here we are also discussing this unusual thing. Like if you go there, so below this pin reorientation, it's slightly like below 50 Kelvin. I told you there are transition, right? So this was behaving. Still, we don't understand this broadening of this peak. Actually, we actually don't understand. So maybe it's associated with the other transition or other kind of ground state. What is there? We really don't understand in detail.
Do you have a quick question or it's okay? Whatever you very quickly ask. Go ahead.
Yeah.
You showed some more subtly around
Raman.
but did you not see something similar around 40 where you have
40 actually, okay. We did not have the setup like sensitive setup below 50 like till liquid helium temperature. We have done one experiment with collaboration with Abhishek from IIT Chennai, but their resolution was lower, so we could not get any kind of transition near that. We expect some kind of, means this origin of this transition is still not clear, why the transition is there. So I was expecting something will happen there, but we could not detect it. That is what I can say.
Sorry. Very nice talk. Sir, one question. You said there are signatures of non-collinear physics. Was there any observation in the Hall effect?
Like collinear, you mean the?
You said from the calculation there is non-collinear physics.
That's what like it's a ground state. Ideally, you if you see the magnetization data, the z axis in the c direction. Now only from calculation or some other measurement, I am not sure what measurement you can do. This non-collinearity, maybe neutron is one of the thing, but I am not expert in neutron. But why neutron was not done in this material, I am not sure. That can only tell you this non-collinearity. So this is only from the calculation they found a two state close by, collinear and non-collinear state, which is 10 milli-electron volt separated. So it's a kind of this temperature matches. So but still I am saying that DFT is still difficult because it's a metallic system and correlation is important. So getting it, I think doing DFT is, I think DFT person can tell more in detail. Yeah, Tanmay can tell more in detail maybe. Yeah.
So let us thank Apindra once again for this wonderful
Thank you.
talk. And let me invite the next speaker.